Yes. Hello. Yes, I'm here in front of many free places, so everybody's at the Jahresrückblick. So, and you are the persons who really are interested in this topic. I hope, or you are the last who cannot get inside because it's full. Okay. Oh, this way. Whatever. I want to talk about privacy-enhanced event scheduling today. And before I start with a real insight, what I mean is I want first to define what privacy-enhanced event scheduling means. So event scheduling itself, maybe some of you know from several applications. So some of you may know this Thunderbird, or we have here something which is from Evolution, which is quite similar to the Outlook client where you can schedule some events. This one is probably well known. It's the Doodle application, which became very popular in last times. And here we have a new application from the German Post named Zeitfinder. And all these applications have something in common. You give them your availability pattern, which is the pattern when you are available at certain timestamps, and then you can calculate the day or the time slot where everybody can participate in some event, and then with this thing you can schedule some event. So these solutions all share two privacy problems. So the first one is the direct inference. This is what you can directly read out of such an availability pattern. So for example, we have here the availability pattern of John, and John's wife may ask, yes, so will my husband just vote for the date on our wedding anniversary? And she can directly go into this doodle poll and look, okay, here's the business dinner, and he prefers to go to the business dinner instead of doing something with me. Okay, so the next thing is the indirect inference. This is what happens if we connect two or more sources where we can get information. For example, here we have two calendars. One is taken from the Sunbird, and one other is a doodle poll, which polls about some chat. And maybe the boss of John can ask herself, hey, this availability pattern of the user Bunny23 looks quite similar to the availability pattern of my employee John Doe. So, and with this, you can, at the first thing, get some information about this pseudonym, and then get information about other availability patterns he do not have in his calendar and these things. And when we talked about these things at the meal at a colleague of mine, so we were sitting there, and his wife was sitting at the table with us, and we talked about this, and she said, yes, every time my boss is unavailable, I'm looking into our calendar, and I'm looking who has an appointment of the same size my boss has, and from there she can infer who is in the meeting with her boss. So, and this is directly, this is the indirect inference you have with these polls. So, after defining the thing, so what we want to have, this privacy-enhanced solution for this problem, I will go a bit more in this problem statement, what it distinguishes from e-voting, because from the first thing it looks a bit like some e-voting solution we already have. Tell you the scheme afterwards, some extensions, and evaluate it, and hopefully come to some demo afterwards of a first implementation of it. So if you have questions, I will stop at these topics every time, and if you have questions, so please don't hesitate to ask. I think we have enough time to answer them directly so that you do not have some understanding problems. Okay, so at first we have some requirements. And the first requirement we have always is we have an untrusted server, because with a trusted server we can solve all the problems. He takes all the dates, all the time slots, and afterwards says what is the best time slot. From this untrusted server, with no trusted entity, there come other problems. Two contradicting requirements, which are, at the one side, we want to have a privacy-friendly solution so that nobody can see what we've voted for. But on the other side, the contradicting thing is we want to have the verifiability, so you want to see what the others have voted, or at least want to have a proof that they haven't cheated the protocol. So this is something which already occurs in e-voting solutions, and we will talk about this later. So, and the last two things are, at the one side, we want to have few messages, which makes the whole protocol more usable. So think of a protocol which needs about 10 times you have to sign first the message, so then wait 1 hour after everybody signs something, then you have to send a message back, and you have to do this and this. So this would lead to an unusable implementation. And of course, we want to have a low computational complexity. So I talked a lot about the thing that is quite similar to e-voting, but it also distinguishes from e-voting. I will show you what is the difference. So in e-voting, we typically have solutions which look like this. So we have a voting ballot where we have many candidates, and you can make one cross at one candidate there. So sometimes you have 3 votes, so then you make the e-voting scheme 3 times, all these things, but they are optimized to scale in this dimension so that you have many candidates. In the event scheduling thing, it's a bit different because you have really many time slots. So think of an extreme example where you have want to have a telephone conference in the next 2 weeks, and we schedule the meeting quarterly. So you have an 8-hour working day times 4 makes times 2 weeks makes 320 time slots. And everybody wants to give his really fine-grained availability pattern to this to calculate the optimal date or the optimal time slot. And therefore, this has to scale in this dimension. So it does not apply directly that we can make several instantiations of the e-voting scenario. And one other thing applies to the e-voting thing, because if you think of an e-voting scheme, it typically has to be applied to 80 million Germans or to millions of inhabitants in the United States or anywhere. So therefore, it has to scale in this dimension too, which is a difference to the event scheduling to our thing, because we only have small groups of 5 to 10 people, and these want to schedule something. Or maybe we have then some other applications in mind, maybe so to vote for what is the cinema film we want to visit, or these things. So after this explanation, after this start, I want to explain you the scheme. So don't worry, it's not so complicated as shown here, and I will only explain you this part. So I will try to make it really understandable. And for the first thing, I want to recall to cryptographic primitives. So first one and afterwards one other, which is the main idea of the whole protocol. So the primitive I'm talking about is superposed sending, also known as the DC network, which was introduced by David Chaum as the Dining Cryptographs problem. So this is a protocol for sending a message anonymously. So think of three people, Alice, Bob, and Carol, who wants to send a message and want to be anonymous while sending this message. So the first thing what they do is everybody exchanges a key, which is just a random number. And when we look into one such key exchange, Alice and Bob store the pairwise inverse number of this key. I excluded the modulo things here to make it a bit easier to read, and skipped some math inside, but the thing is that we calculate in some group and they store the pairwise inverse number. So afterwards, after every participant exchanged some key, we have on this slide once the KAB in the positive form and once minus KAB, plus KBC and minus, and here is minus KAC and plus KAC. So every number is on this slide, once in the positive form and once in the negative form. So when we now want to send the message, everybody takes this message and adds the key to the message or subtracts it in the way. So when now sending this message to some single server or distributing it under the participants, you cannot infer on this way if there is some message inside or which message is inside, because this message is encrypted with these two numbers in a in an unconditional strong way, because this acts like a one-time pad to the message. So you cannot see who sent what. But when you add all the messages up, you see that we have once the positive and the negative element of this key once there, and so these two will go away, these two will go away, and these two will go away. And what is at the end on what we have at the end is the sum of all the three messages without knowing who sent what in the whole scheme. So, and this is afterwards actually what we want, but this is first the cryptographic primitive which was introduced by David Chaum. So, and now we come to the protocol. The protocol has several phases. We start with some poll initialization, which is similar to this initialization at a Doodle server. So you go to some web page and say, okay, I have some time slots and some voters. In difference to Doodle, you have to specify the voters, so which is afterwards your anonymity set of the people who will participate in this poll. And you or the server will send an email to everybody, hey, this is the link to our poll, and these are the time slots where we want to schedule some meeting, and these are the other participants. So afterwards, everybody exchanges some key. And when we look into this key exchange, it looks quite similar to what we have seen now. So Alice and Bob exchanges the key, where Bob stores the negative inverse element of this key, but we have not only a key, but we have a key vector, which is not one number, but we have several numbers. So, and we have one number for every time slot we exchanged, or we configured in the initialization phase. So after exchanging the keys, everybody sends his encrypted vote to the server, and this encrypted vote looks like this. So it's a vote vector where is one encrypted vote for every time slot, and in for every time slot we take our actual vote and encrypt this with the keys we have exchanged from the others. So this actual vote is an element, of course, an element of the group we calculate, but it is defined to be only valid when it's 0 or it's 1. So 0 means I cannot participate at this time slot, and 1 means I can participate. So after everybody voted, the server sends us an email notification with the missing vote vectors we also need, and from this we can calculate the result of the vote, because we now can build up such a matrix where all the vote vectors are on the matrix, and when we look at one column, we see that we have here the vote we encrypted, the first thing. The second thing is the vote Bob encrypted, and here's Carol's vote. And again, we see that here is every vote vector, every key, once in the positive form and once in the negative form. And when we add all the three vote vectors together, the keys will go away, and what we get is the sum of this column. And this is actually what we want to have, and we get the sum from this without knowing who voted for what. So, and when we do this for every column, we choose the time slot with the highest sum, and we are ready. So, really ready? No, we can try to cheat. Who has something where we can cheat? Who can see something in this protocol? So we have this, so the Web 2.0 programmers of you should scream, no, there is some user input, and user input is every time bad. Because what the voter can do is just send something different than 0 or 1. I said it's an element of the group, and we have to calculate in some group. We cannot take only a binary number here, because for this calculation and for the calculation later on, we need a group which has the modulo which is higher than the number of participants in our vote. So if we have 10 participants, we need at least the modulo, calculate here modulo 10 or modulo 11, and therefore you can choose here any element from 0 to 9.
But maybe it's okay to have maybe 0.7. So I say, oh yeah, it's pretty good that I will attend, but I'm not really sure. So I say
Yes, okay. We can think about this later if we can try to do this as a feature, but yes, this would be really a problem because what means when sending here, so we can use instantiate two values, so we can send a -1 and a 2 here. And what is the meaning of a -1 here? If we have modulo 11, the -1 is 10. So then you have to say something like, okay, you can say from 0 to 5 or from 0 to -5, and the cheater can always say the most negative value and then cheat the others that every time comes 0 and these things. So yes, you have to be really careful, and we have to look at this, what happens here.
You need some match checking before doing this.
Yes, we need some checking, but the problem is we encrypt the vote afterwards in an information theoretically secure manner. So we cannot have a verification with this encrypted vote. So, okay, everything okay until here, or are there more questions for the understanding? So then, remark that I only have to look at this vote, and we do not have to look at if we cheat with these keys, which are user input as well, because cheating with a key would be the same as cheating with a vote, so we can add these to the others. Okay, so we want to investigate two things. The one is I send a -1, and the next thing is I send a +2. Because if we have looked at these two cases, we have every other case where which is then only an extension of this case. So the first thing is we want to avoid -1 cheaters. I have here a table where only the clear votes are written. And we see we have this vote where Alice voted 1100, and we have the sum at the bottom. So in this case, we would choose this second time slot, for example. But maybe Mallory doesn't want to take the second time slot because there she's not available, but she wants to have the third time slot, which would be much better for her. So what can she do? The first thing is, I said, she can send just a -1 there. So, but what happened now? When she sends a -1 on every other time slot, on the last time slot, a -1 occurred. So, and this is, of course, you will see this in the output because the sum cannot be a -1. So it's only valid if it's in the range from 0 to the number of voters. And one other thing would occur here, the 0 would be detected too because Alice knows she sent a 1. So, and if she sent a 1, for her here, the range should be 1 to the number of voters. So, but yes, we can argue with a little knowledge about the things of the other. Mallory can guess when the others are available and send only a -1 here, and she would win and the 2 is there. So with this little knowledge. But what we've seen now is the problem for Mallory was she has to guess where the others sent a 1. So, and we can try to make this harder for Mallory in a way that everybody distributes his vote vector into several tables so that Alice says, okay, I want to send a 1100. We take 3 tables at the end where I send in the first all zeros, here this one and here's this one, and in the sum I get my vote from Alice. So Bob is doing the same. So he has here a 1, here a 1, and here all zeros. And what we achieved with this is we just made many zeros, which are really randomly distributed along many tables. So think of 100 tables here. So, and we can ask ourselves, the sum of every table should be higher than 0. And for the calculation for our time slot, we only take the sum over all tables, which you can calculate. So this makes it really hard for Mallory because she knows what values she can send here, but this value she does not know. She has to guess where she will send a -1, and this is 1/3 here in this example, and this of course has to be a bit higher then. So and with this trick we can avoid the -1 cheaters. It's okay? So yes, but we said, okay, there's another way to cheat. Here, for example, she can send a 2 at this stage. So, and what would be the problem then is that when Mallory sends a 2 here, she has to make assumptions about their voters at the other places too, because she only guesses that somebody else sent a 0 at this day. So, because otherwise here would be in the sum a value higher than the number of participants. So, and having this trick in mind with the -1, we can avoid the +2 cheaters too, with making not only the normal poll, but everybody has to send an inverted poll as well, where everybody has to invert his vote. So Alice has not only to send here the 1, but she has to send here a 2. Here was a 0 from Bob, and here's a 1. And Mallory has sent a 0 here, and here a 1. So the sum of this is a 2 afterwards. And from the fact that this poll is the inverted poll of the normal poll, we can see that the sum of both sides should always be the sum of the number of the participants. So with checking this sum, we can enforce that everybody has to send really the inverse of his element. So in the next column, we have this 110, 001, and the 3. And here is the problem for Mallory, because here was 012, and she has to send a -1 in this place, because otherwise this would add up in 4 and not in 3. So, and when we distribute this inverted poll into several tables, as we have done with the normal poll, we can avoid the -1 here in the same way we have done before. So therefore we can do the same trick with the -1 as we have done for the +2 as we have done for the -1.
Can you tell who is the cheater?
What?
Tell who is the one cheating.
Okay, the question was how to tell who is the one who cheated. So at the moment we cannot tell. I can tell you later on, I've skipped in this presentation the trick how to tell who has cheated, because I thought it's a bit more simple. But I can show you afterwards how to find out who has cheated. So because if we cannot see who has cheated, you can attack the availability of the poll. So then you can block the whole polls anonymously. But we can avoid this with afterwards. I will show you afterwards. Okay, so other questions up to this moment?
If we go back maybe 2 slides, there was the with the 1.
Ah, the -1 cheater.
Yes, the 1. But on the right side they made the sums of the yes. So it's okay. But if for example the Mallory knows what Bob voted, because she knows him, then she can fake it.
Yes, for example, she knows that Bob voted a 1. So then she knows she can send a -1 without risk.
Yes.
But Bob distributed his 1 under several tables. Think of 100 tables, and there's 1 in 100 tables. So she has a chance from 99 to 1 to win this, to find out the 1. If Bob really distributed his 1 randomly over the 100 tables.
Why randomly? So
Because this is the protocol. He has to.
Alice, maybe Mallory and Alice live in the same flat, and he knows what she does because he talks too much.
So okay.
So he knows what to vote.
Yes, no. Wait, then we have Alice and Mallory cooperating. So, and if they two cooperate, so
Maybe Mallory spies on Alice and has some intelligence information about Alice, and then he knows or she knows what's to vote.
yes, but if Mallory knows exactly the votes of Alice, then she can calculate the votes of Bob from this fact. So the privacy is broken with this, because you can calculate all the votes from Bob.
More participants, and you have
If you have 10 participants.
information of about one participant. So you can compensate this participant because you know what he voted, and so you vote against.
Yes, of course. If you have, for example, a Trojan horse at Alice's computer, so then of course you know where Alice sent the 1, and then you can manipulate this. But if you have a Trojan horse at Alice's computer, you can just send here a 0 and you're ready. So okay.
So this doesn't work for Alice because your own Alice is old,
No, there's no need to compensate her. If you have a Trojan horse at Alice's computer, you can just send a 0 here instead of a 1 for Alice.
Okay.
So, and then you have the same achieved as sending the -1 yourself.
But it won't be will not show to the others because others will not know that you have compensated because it can make a perfect cheat if you own time.
Yes, so if you have a Trojan horse at Alice computers, of course, you can cheat with Alice vote as you want. You can do everything. That's of course. That's for sure. Okay. So then, we have some extensions because, yeah, okay.
Is there anything that hinder your system to use with continuous ranges instead of discrete ranges? Right now you choose 0 or 1, I cannot. Is there anything wrong saying 0.6, I mostly can?
Okay. So the question was if it's the same question we had here, if the scheme is applicable to not only a binary choice of 1, 0, or maybe one can make a choice of 1 to 5 or even 1 to in 0.1 steps to 1.
I want to have it between 1 and 0, so I still have a range I can log.
So yes, but so no, that's not the direct application because this calculations every time in some group modulo some value. So and there you have no.
For example, when people have the maybe option.
Yes, yes.
You could do that by just having 2 time columns.
Yes, yes, that's what he said before. So allowing the 0, 1, and 2. So and everybody can say a 2 for this thing. I don't know if it's the thing you would like to implement the maybe option, because if you want to have this maybe option, I would prefer to have a separate vote for this one saying, summing up all the maybes. So, and implementing anything in this way. I haven't thought about this, but I think one can solve this with summing these extra up.
Another problem is also when you have several different scheduling taking time and things like then you can have one that needs to block all the other available times.
Yes. What you're now talking about is so side constraints between several applications. So I can only make one here. Yes, but of course this is a problem which is the constraint satisfaction problem in many other protocols which are really more expensive in terms of calculation and message exchanges. But I do not want to target at this problem because I want to have a simple protocol which really allows an application like Doodle, like this thing. So and there, okay. So. But now we want to look at some extensions because one thing is a bit pity in this protocol. So we have this key exchange here, and this key exchange scales quadratic in the number of users. So we do not want to have this. If we have 10 users, everybody has to send an email to every other and hey, please, we have to exchange keys and send this with GPG encrypted and these things. And so we do not want to have this. I think everybody sees. And if we could skip this, we have really the same protocol as we have in Doodle because we have this first initialization, everybody gets an email, everybody sends his vote, and afterwards everybody has voted, everybody gets an email, hey, this is the result, great. So, and yeah, of course I have a way to skip this simple, this key exchange. And this simplification works with Diffie-Hellman, which was mentioned before in the talk. I want to explain Diffie-Hellman key agreement shortly beforewards, even if some of you knows this, because I think not everybody knows this. So Diffie-Hellman key agreement is based on the discrete logarithm assumption. And this assumption says, so first we have here the discrete logarithm, and which is the normal logarithm we know from school modulo some prime number. So, and the assumption says, even if I know the x, which is the calculation of this whole, the g, which is some number, some generator, and the modulo q, even if I know all the 3 values, it should be impossible or hard to find this r. So of course, this only applies to big numbers, and there are some assumptions on this, but this is the assumption you should have in mind. Okay? So and based on this assumption, the Diffie-Hellman key agreement works as follows. So we have Alice and Bob, and they want to exchange a symmetric key over some untrusted thing named internet. Yeah. And they have all their trusted areas, which are here marked gray. And the first thing everybody does is they exchange some public things. So they agree to some generator and some queue, which is afterwards actually this generator and this queue. So everybody chooses some random number. Alice are A and Bob are B, and everybody calculates this exponentiation, G to the RB modulo Q and Alice to the RA. Afterwards, this X is exchanged, and from this value, everybody can take his randomly chosen number and calculate XB to the RA or XA to the RB. So if we look at these things, what is inside here, so inside this XA, there was the G to the RA, and G to the RA to the RB is the same as G to the RA times RB. So and the same is on the other side, because inside this one was G to the RB, and G to the RB to the RB is the same as G to the RB times RA. So with this protocol, both calculated the same value here, which is afterwards the symmetric key. But when you look from the attacker side, who knows everything which is in the white here between, he knows XA, G, and Q, which is the same as here, X, G, and Q, and he knows this value. But what he cannot calculate is the RB and the RA. These two secret values, and these are needed for this last calculation. And based on this assumption, both can agree to some common key over some untrusted area. Okay? So, and we can use this and simplify the key exchange with skipping the key exchange, but replacing the key exchange with some registration phase. So we have some registration, which is the Diffie-Hellman thing. So everybody sends some public key, which is G to the RA, or to some random number, to the server. Of course, here's the modulo. I skipped the modulo again. And afterwards, the server has some registered users. And when we make the poll initialization, we do not send the strings, so Alice and Bob and this will participate, but we send the public keys of these people. So, and afterwards, everybody has the public keys, and maybe you have seen, so that this G is the same for everybody. And of course, the Q is the same for everybody as well. And from this fact, everybody can calculate the common keys from this public key with his secret R. So, okay. Okay. So, and here we look at how this calculation is done. So we have this dashed arrow, which is a logical exchange. So I marked here some logical thing where we want to calculate from this Diffie-Hellman secret, which we just calculated in the way I explained Diffie-Hellman beforewards. And from this one, we want to calculate this vector. So let's look how this can be done. Of course, we have to put this inside some deterministic pseudo-random number generator and get from this what our vector. But as I said at the beginning, this vector is some key for every different time slot. So therefore, I have to include this index into the input of the pseudo-random numerator to avoid getting the same key for several time slots. So, and of course, I have to include some UUID, which is for this poll, because it may occur that we have different polls which have the same time slot, and if I do not include this, we would end up with the same key and these different polls. And something else, which was not at the beginning, I skipped this at the beginning, but I introduced this later. We need some indexing the tables, because we split it up in many tables afterwards, and we need this too. So, and with this pseudo-random number generator, we can generate from our Diffie-Hellman seed all these keys and use this for the calculation later. Okay?
What about the algorithm and the pseudo-random generator? So is the algorithm public or is it closed?
Of course it's public. So this one,
If you have the inputs, you do not need the key exchange. You can do it on your own if you take the same pseudo-random generator. Because
no, you do not have this secret. So
you don't have to, okay,
everything belongs on this secret. Yes. So and this is also a bit a simple product, a simple thing. I've written a more complex thing here where I explained what assumptions we have to put on this pseudo-random number generator, and we have to use some hash function between, which is needed to know who has cheated when we see this -1, which I said. I can fetch the slides afterwards if you want to see this. Okay. So then we have some other extensions, because we want to make the scheme a bit more usable, and it may occur that we have started a poll, and after it started already, somebody says, hey, I want to join this poll, I want to join this meeting, I want to also participate. So, and it's a bit of a problem, because we have now here our group, he wants to join, and maybe somebody already voted. So he already sent his vote. So, and this is a problem for this protocol, and we want to have this. So, but we can, it's not a big problem, because what we simply can do is, after he has voted, the key exchange is defined in this way. So we have such a key graph where he has calculated inside his vote a key with Alice, and this is Mallory, for example. So, and when now this person wants to join, he just calculates all the keys with persons who has not voted yet. So, and we have not a full key graph afterwards, but this link is missing from this person to this person. So, and with this extension, we can just use this dynamic joining. So, and another extension may occur. So think of all these 3 persons have voted, and they see, okay, Alice is on holidays or anywhere else, and she will not give her vote. So, and now we have a problem, because we have unconditional, strong, encrypted votes, and we cannot see what is inside the votes. We have to ask everybody again, yeah, let's restart the poll, and there's a problem for this, so what to do now? So, and the good thing is, we can do this without restarting the poll, because everybody, but also we have to ask everybody, but everybody has to agree to this anonymity set reduction, because so beforewards Mallory would be inside this anonymity set. Ach, schwieriges Wort. And with releasing the keys for her, we can calculate some additional vote, which has a 0 in every time slot. So, and with this additional vote, we can just calculate the sum of everything, and we're ready. So, and now think of not 10 persons and 5 at the beginning, 3 have voted, then 3 are joining. From these 3, 1 doesn't voted, and these things. So we have a really complex key graph, and then afterwards maybe we have to ask 4 persons for their key, and then we can decrypt everything. So maybe such a situation may occur.
if the persons are equal, don't provide the keys.
This is a problem. Of course. So because at the beginning we've configured our anonymity set in this way that we have all the persons inside, and we said, okay, nobody should see what is our vote without, so our attacker model is all n-1 people from us has to cooperate to see this. So, and if we have one who does not cooperate, of course. Okay, so if there are no questions, we can look if everything holds what I've promised. So I had some requirements at the first thing. The first one was an untrusted server, which we of course have fulfilled because we only need the server as in blackboard. And the only assumption, to be honest, is on the server is he has to hold every message back before everybody voted. So what could occur is somebody cooperates with the server and gets the message before he votes, and then he can see the sum before he votes. So he can see the result before he votes, but he also cannot break our privacy. But he can do this one. If we want to get this assumption away, we have to use one more communication round where everybody encrypts his vote, sends it, and afterwards decrypts after everybody has sent his encrypted. But we have no other assumption on the server, and I would say it's for the privacy, it's really no problem. It's really good. So the next thing was the privacy, and I think we have fulfilled it as well because nobody sees who has voted for what. Only our attacker model was that n-1 has to cooperate, and if n-1 has to cooperate, we can calculate our vote with any scheme because then we can just subtract the sum of them and then we have our vote vector, so it's not possible in other way. So this verification we have achieved with splitting the vote, first the -1 voters and then inverting it and therefore avoided the +2 voters. So the communication steps, we have the same as in Doodle, so we have, as you calculate 3 or 1.5 if you calculate in both way, communication steps. And for the computational complexity, we have a scheme which scales in the number of dates, so it's we need p-1 asymmetric operations per voters, which is one Diffie-Hellman calculation for every other voters, for every other voter, and that's it. So the other calculations are all symmetric, which are really cheap. So, are there questions?
You still need a trustworthy server?
No. So it's the thing, the question, what is the trust you place in your server? So for the privacy, you don't need any trust with the server. But for, yes, only for this, you can see the sum, what is, of all votes before you vote.
And the server can manipulate the result.
Okay, if you mean this one, therefore you do not only need a trusted server because every attacker who can manipulate the line can just add 1 to your encrypted vote vector, and then so we have this vote vector. Wrong. Here, and no, I do not mean this one. This one. And everybody can add a 1 here, and this one addition of 1 here would add up a 1 here, and would be then make from a 0 a 1 or from a 1 a 2. So this can be done by everybody, not only from the server. But I avoid this with everybody signs just his vote vector, and everybody checks this afterwards.
But you still have to trust that the server correctly computes the sum.
No, because you get only all the vote vectors. You check if these vote vectors are correct by checking the signature of Bob here and Carol's signature here, and afterwards you can do the calculation your own. Okay. But it's good that you think. There. No, here. Yes. So, are there questions? So then okay.
Feature requests, so to say.
Okay.
If you want to implement a policy that legally some people are more equal than others, so they have more right, if they say, maybe the...
Yes, okay, I wanted to come to this later on. I have this feature also inside, this feature request. In my Outlook, I have some features which I want to have later on, but I have some solution for this. Okay, so I partially implemented it. It's pre-alpha state. And you can achieve this at, I wrote this at doodle.inf.dresden.de because I'm coming from the Institute of Datenschutz und Datensicherheit. Yes. So you can achieve this here, and there should be any link. No, I forgot this link there with privacy enhanced. So you get the privacy enhanced version, and you can try this. But it's not everything implemented in it. But for example, we have the meeting, and we create some poll here. And everything is implemented in JavaScript. So it should work with any browser who is applicable of JavaScript and HTML5. So you need HTML5, sorry. I can show you for what later on. So, and we configure some dates, so some time slots, the 30th and the 31st. And here we have to invite some participants. Of course, I show the user strings for this, but when we look into the source, we will see that that we have behind this, we have to send the public key, or this is the fingerprint actually of the public key from Alice. So, and sending this, we configure, okay, Alice wants to participate, and Bob as well, and maybe Carol. And afterwards, we send this link around, and everybody goes there. And then you have this scheme, which is quite the same as in Doodle, and you can say, okay, on this day, and I submit. And what happens after when I press submit here is, in the background, there was already a calculation of this vote vector for this time slot. And when I press submit, it just submits these vote vectors to the server. So, and we can look now into the server here. Yeah, make it bigger. So, and when we look here, you see, okay, yeah, here is it. This is the vote. So this person with this key voted for these three columns, and the first was this long number, and the second was this number, and the third was this number. So you cannot see anything from this. So, and when we now, when we go now back to this, and of course I log out as Alice, and I log in as Bob, and you see here as password currently you have to give the secret key, which is quite long. This is a bit of a problem. Yes, I'm not sure how to solve this, to have here a short seed and calculate from this short seed the long key. There are several ways to solve, I know, but yes, I'm not quite happy. So, and when I log in, it's not a login. I've only made such a login to show the normal feeling a user has. So the only thing which was done now was calculating from this secret key we entered here, so the public key, which is this one, and fetching this modular, and just an initialization, so there's no server round trip with this, pressing this. But now we can go to the meeting, and the browser detects that I'm Bob and calculates the keys in the background. And while it's calculating, of course, I can just vote. And yes, you see JavaScript calculation is not very fast, but when it shows the submit button, I'm allowed to submit this. So, and now we too have voted, and we see, okay, now we want to kick out Carol because she is on holidays or anywhere, and we press this kick out button, and I'm asked, yes, do you really want to remove her? And when I press this button, my client sends the key from Carol to the server. And now the server has the key from Bob, so therefore it says, okay, there's the key from Bob. Bob wants to remove this participant. And I can go back, log out again, and log in as Alice. Log in, and go there. And now I see, okay, Bob wants to remove this participant, but it's currently calculating the key. And when the key calculation from Carol is ready, because I deleted it, I can say, okay, yes, I agree to remove this participant. I remove him, and hopefully we will see who has voted for what. So yes, that's it. So, what is not inside currently is the thing with the tables and the thing with the, okay, 10 minutes, the thing with the recognizing who has cheated and these things. So there's a lot of things to do, and currently you have to trust the server that he delivers the right JavaScript code. So because there's no mechanism as we have in Java applets that the server sends some signed JavaScript code. So at least I know none mechanism in this way. So the solution I have some students at the moment who implements this as a Java thing. So then you can download the Java source from an external web page where you trust the developers of this, and then you can vote on these things. Yes, so there are some issues, but at the end it should work, everything. So we can skip the things here and come to the conclusion. Yeah, so it's a novel scheme for privacy-enhanced event scheduling. It scales in the number of time slots without any central trust. I already implemented it, and what I want to do as next is, of course, I want to implement the missing features, then make some performance measurements. So because there are other schemes which are really e-voting schemes you can find in the net. So, and just look how this scales against this one. And I have some more features, I already said. So, and as you already asked for the features, I can show you what's, the thing what I want to do is, okay, at first, of course, I want to mix this, that you have at the top this privacy enhanced version, and at the bottom for all the people who do not want to have HTML5 or do not want to use this and whatever, do not want to wait, use this version. And of course, what you said is, I want to do some complex decision rules where you can say, okay, so because we had this problem, so we had some doodle poll and from 13 participants, and we needed some telco, and of course the date with the most participants was 9 or something like that. So, and they said, of course there are 9, but at another time slot there are 8 participants, but from every institute, so we had the Frankfurt Goethe Institute, IBM, and some other universities, and they said, okay, from every institute, some other, there are participants from every institute, and I want to do this with some, again, more tables in the background, and do several polls with this, so that you have below more than one sum, because of course you have now less features for the decision at the end, because it's privacy enhanced. Okay, so this is then in addition. So I think we don't have time to show you how I can prevent how to detect the -1 cheater, but I can show you in 4 eyes, I think. Or if you don't have questions now, are there other questions?
Can you detect the class 2 cheater also?
Yes, of course. Like the -1 cheater.
Is it possible to implement the deadline instead of, because it's
Yes, of course.
someone doesn't know,
Yes. Of course, it's possible in the first thing to just implement some deadline where everybody gets an email. This is easy. But what I thought of was something like a threshold scheme, but I have no idea how to implement it at the moment. So that saying, so if 60% voted, we decrypt everything. But I have no idea at the moment. But I will think about this.
This would be even because maybe some people are very quick and they overvote the slowly drift. And so
Yes, maybe.
Could be even, especially if you do something by automatic means.
Yes, of course. Kicking out voters is evil anyway. So because think of you have Alice, Bob, and Mallory, and Mallory holds Bob's vote back and says, okay, please kick Bob out here, and Bob already voted, and no, he's not available, please send me all the keys from Bob. Yeah, I can decrypt his availability pattern afterwards. Of course, you can do such things. Yeah.
So, have you looked at, because you implemented it as a Web 2.0, but I like Internet 1.0 things, so I think with instant messaging. So because you can have all the people real time online, do all the negotiations real time, just do a sweep over the whole calendar to do a pre-calculation in front of...
Yes, of course, but so for the stream, the question was if doing this inside an instant messaging application, so to do it in real time and to make to not have the constraints of this message exchange and these things. No, I have not looked at it because I do not want to have such a scheme, because I think it's a more common scenario that the people just go to some website, want to click something, and then it's away, and they do not want to install something. So this is, for us, of course, it's valid. For us, the geeks who wants to install this and say, oh yeah, great, I have this cool new thing, and it integrates into my Java, it's an extension specified in XMPP, and great. And,
well, actually it makes sense, because people in the corporate environment will have something like exchange, do that for them. You can do mapping, lots of interesting things before you make people vote on stuff, so that you don't bother people with having to do all kinds of voting.
yes, of course, I see this scenario, but I think the more general thing which reaches more people at the moment is such an application which just runs zero footprint out in the browser. So, because then you can, of course, think of an Outlook plugin which just manage everything in the background and these things. Of course, I think you can do this. Yeah. But I first wanted to look at these things, yeah.
What's the license of the code?
It's all GPL. It's 8GPL 3. Okay.
What about the feature for the boss or the nobleman to be more than the other people?
Yes, so I thought this feature is included, so the question was about a feature that somebody count more than others. I thought this feature you can express with this feature. So if you have these 3 people are worth 3 and these 3 people are worth 2, and afterwards you have the sum of all the worth 3 people, and you can calculate this times 3 plus this, and then you have this, the current thing.
Okay, but you have to put them extra. So maybe
Yes, and, okay, I not thought about making this really explicit inside this.
that everybody has to buy his votes from the server. And so the richest man might buy 100 votes, and he can vote 100, and the poor man only can vote 1.
Yes, but do you want to have this such a
Then you
scheme?
have the number of the votes that are on sale, and then you have the number of votes that are sold, and then you can say, okay, from the sold votes, I do the summing stuff. So if somebody bought maybe 20 votes, then you don't put 1 or 0, he puts 20. And then you have to calculate with 20.
Yes, but then you have then you have many other things where you can attack the scheme. So now, because then you allow this +2 voter and this +3 voter.
You have to put this in the calculation, so that somebody bought 20, and then you have to adjust the calculation in this way.
So yes, I think one could think about this, but I don't know if it's a valid scenario which we want to have in the real life, so I don't know.
The most straightforward way, of course, is to give your boss 2 or 3 accounts.
Yes, of course. Give him 3 accounts and then he can vote 3 times. Yeah. So, okay. So, then I thank you for your attention. And, yeah.